across the secondary winding is equal to 220 volt. So this will be your answer. So basically this is the end of your chapter. From my side, that is AC. Eddy current was removed from your syllabus, so that is why I am not touching that part. Okay, basically this is the end, but we will discuss one more thing with energy losses. We will discuss here. Okay.
Okay.
So after this, we will this chapter will be finished. Okay.
So
now
can you explain from the second part of the answer?
Second part is very easy. Okay. Actually, see here. Basically,
the secondary voltage. Can you explain that?
I'm just doing it again. See, basically, see this first this formula.
Yeah.
So can I use this part of the formula?
Yes, sir.
Okay, now we can use this. So now tell me what is secondary voltage? See the secondary voltage. We have to find the secondary voltage now?
Yeah.
Okay, so we have to find the secondary voltage.
Yes.
What is the primary voltage? This is 220 volt.
Yeah.
This is the primary voltage. Okay.
Yeah.
So 220 volt. Now, what is the number of turns in the secondary coil?
200.
Secondary winding 200. So NS is equal to 200.
Okay.
Number of turns in the primary winding is equal to 100.
100. Yeah.
You can see here.
Yes.
So this data we have.
Yes.
And we want to find the secondary voltage.
We can. Yes.
Now put all the values. So secondary voltage we want to find. Primary voltage is given as 220 volt. Secondary number of turns in secondary coil is 200, and number of turns in the primary is equal to 100. 100 and this cancel out is equal to this 2. So when you will multiply 2 with this, it will become 440.
440. Yeah.
So ES is equal to 440 volts.
Okay.
Now you can take the screenshot. Then we will discuss the energy losses in the transformer.
Okay. Done.
Done. Okay.
Yes. Done.
Done. Okay. Energy losses is a basically what are the types of the energy losses will be there in transformer. Okay.
Okay.
So energy losses in the transformer. First, you should know there are 4 types of energy losses: flux leakage, resistance of the windings, hysteresis loss, and eddy current loss. So one by one, I will discuss. This is a theoretical topic. What is the meaning of the flux leakage? Flux leakage means, see, what is flux? Basically, the number of magnetic field line crossing the coil. So here are these magnetic field line, but in case of solenoid, the magnetic field is not perfectly axial. It will be like this, okay? Magnetic field is like this, okay? So this is the magnetic field. So if this is the magnetic field, so these lines will not be straight lines. Magnetic field lines will be not straight. So there will be some flux leakage here, okay? There will be some flux leakage.
Yeah.
Okay, as the magnetic field is not perfectly axial.
Yes.
There will be some flux leakage.
Yes.
Okay. For that flux leakage, for minimizing that flux leakage, what you have to do, you have to align the magnetic field line in a proper direction like this. So that is why we use the soft iron core, because soft iron core confines the magnetic field within itself. Okay.
Okay.
So first loss is clear.
Yeah.
First energy loss is the flux leakage. How to minimize the flux leakage? Use soft iron
Software.
core.
Yeah. Okay.
Resistance of winding. This is very common. Every wire or every winding will have some resistance, and
Yeah.
due to that resistance, there will be the heat loss or energy loss,
Yeah.
and that
Energy loss.
energy loss is given by I square RT.
Okay.
How to minimize this? Simple. Decrease the resistance. Decrease the resistance of the winding. And how
Yeah.
to decrease the resistance of the winding? Use a material which have low resistance, like we know copper.
Oh.
So copper
Yeah.
is a material having the least resistance, but copper is costly.
Yes.
Copper is costly, so whole transformer we cannot make whole transformer winding of transformer. We cannot make of copper.
Yes.
Okay. So
Yeah.
basically, what happens? We use a thick copper. We use thick copper.
Yes.
Okay. Thick
Okay.
means the area of the copper will increase. Okay.
Okay.
So resistance is given by rho L by A. Rho is the resistivity of the copper. Resistivity of the copper is very less.
Okay.
L by A. So if you will use thick copper, means area more. If area more, then the resistance of the winding will become less.
Okay.
So if you will use thick copper, means you are using a copper having area of cross section large. If the area
Yeah.
and resistance is inversely proportional to the area of cross section, you can
Yeah.
see here. Okay, area of cross section is large, then resistance of the winding will reduce. So we use thick copper wire on the side of the transformer where the current is high. Basically, whole winding we cannot use the copper because it will be very costly.
Yes.
So we use there where the current value is large. If the current value will large, on the there will be different parts of the transformer. There will be different sides of the transformer. So we use the copper on that side of the transformer where the current is very high, where the
Okay.
energy loss is very high. Current is high means energy loss in the form of heat is very high from this formula. If you will increase the current, the energy loss will increase.
Increase.
Next is the hysteresis loss. Hysteresis loss means uh, so basically, I have told you here is the alternating current, and due to the alternating current, magnetic field changes.
Yeah.
In the starting, I have told you. So
Yes.
basically, as the alternating current changes means sometimes it is maximum, sometimes it is minimum, sometimes it is zero. So due to that, in the winding, there is continuous magnetization and demagnetization. When the current becomes zero, then there will be the
Yes.
demagnetization. When the current will have some value, then there is a magnetization. So due to
Okay.
the magnetization and demagnetization, there will be the energy loss that is known as the hysteresis loss.
Okay.
Okay. And what is the solution? Use the soft iron.
Okay.
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 Now eddy current losses. What is the eddy current? Basically, first we know what is the eddy current. We know that this current is the alternating current, and alternating current changes continuously.
Yes.
Due to the change in the alternating current, I have told you magnetic field changes continuously across
Yeah.
the winding. And due
Yeah.
to the change in the magnetic flux across the winding, there is a change in the magnetic flux across the winding. Due to that, there will be the induced EMF across the windings or
Yeah.
across the parts of the transformer. Okay.
Yes. Okay.
Basically, there is a change in the current continuously across the winding or across the bulk part of the transformer. So due to that, there will be change in the magnetic field. Due to that, there will be change in the magnetic flux. Due to that, induced EMF will be there. So basically, induced EMF will be there first in the windings. There are the copper windings.
Yeah.
Okay,
Okay.
copper windings are there. So first induced EMF will be across the copper winding. Another induced EMF will be across the material of the core. Across the material
Yeah.
of the core means this is the core. This is the soft iron core.
Yeah.
So due to flux will also be linked with the core also. apart from this binding, the flux is linked with the core also. So
Yeah.
when there is a change with the magnetic flux linked with the core, then there will be the induced EMF in the core, in the bulk of the core, and due
Yeah.
to that induced
Okay.
EMF, the current will be induced in the bulk, and that
Okay.
induced current is known as the eddy current. So basically, induced EMF across the material of the core or soft iron, and due to that there will be the eddy current. So basically this is the soft iron core. Basically
Yeah.
this is the eddy current,
Okay.
circular form. In circular form, these are the eddy currents. Okay,
Indicators.
so
Okay.
if there are eddy currents, and due to the current, I have told you there will be the energy loss. So energy loss due to the eddy current is given by eddy current into resistance of the material into time t. So
Okay.
okay, and resistance here we will take the core of core material resistance, because the eddy current is inducing in the core material of the
Raw
resistance.
material.
How
Okay.
to minimize? How to minimize?
You using copper
Laminated core. We use the
laminate.
laminated cores.
Okay.
Laminated core means in parts we will use the cores. Okay, with insulating liquid in between. Okay, so we will use a
Okay.
laminated core like this. For example, like you can see the pages of your copy.
Yeah.
Okay,
Okay.
these types of things we use. If you
Okay.
will see the binding in actual, then you will get to know. Okay, so
Okay, sir.
basically what is the solution for eddy current losses? Use laminated cores with insulating liquid in between.
Okay, sir.
Now we can say this chapter finally. Can note down.
Okay.
So in exam they can ask you. They will not ask you in detail. They will ask you what are the energy losses in transformer, and they can ask what is the flux leakage, and how to minimize the flux leakage. Okay? So
Yes.
accordingly you have to tell.
Done, sir. Done, sir.
Done.
Yes, sir. Done.
Okay, so
Done, sir.
this chapter is finished now. After that, do you know what is electromagnetic wave?
EMB?
EM wave.
No, sir.
Light. We have the light now. So light
Yeah.
is an electromagnetic wave.
Okay.
So
Light
so
wave.
light, light, just light, na sunlight.
Yeah, yeah.
So basically, sunlight is a wave, and
Yeah.
sunlight is a basically a electromagnetic wave.
Mhm.
So name from the name, electromagnetic wave.
Yes.
So in electromagnetic wave, there is electric field and there is magnetic field.
Okay.
Oscillating electric field and oscillating magnetic field will be there in in case of the electromagnetic wave.
Yes.
So electromagnetic wave we will discuss later. First, we will discuss some important aspect. Now write the new heading, electromagnetic wave. So from here, your chapter electromagnetic wave is starting.
From here, sir?
Hmm?
From this slide, right?
Yeah, from this slide, electromagnetic wave is starting. Okay. So electromagnetic wave, I will write EMW.
Okay, sir.
Electromagnetic wave. Electromagnetic wave. This is very short chapter, means short unit, not very lengthy unit. Okay, and before defining what is electromagnetic wave and what are the properties of electromagnetic wave, we will discuss. There was a law, Ampere circuital law, we have discussed, and I have told you there what is Ampere circuital law. Ampere circuital law says that the line integral of magnetic field along a closed path is equal to mu naught into current enclosed by that closed path. For example, this is a wire AB.
Yes.
This is a current carrying wire AB. So if you will take a circular loop around this wire and you will calculate the line integral of magnetic field. We have already discussed these things. So if you will calculate the line integral of magnetic field along this closed path, basically this is a loop, this is a wire, this is a closed path around the wire. So the line integral of magnetic field is equal to mu naught into current enclosed. What is the current enclosed by this loop? This I is the current enclosed by this loop.
Yes.
This I is the current enclosed by this loop. Okay. So basically, what is this? This term is the, you can say, line integral of magnetic field. Line integral of magnetic field along closed path. Along closed path. Earlier, it is given by Ampere. This thing is given by the Ampere. This is Ampere circuital law. But there was a scientist named Maxwell. Maxwell proved that there are some inconsistency in this law. This law is not fully correct. We cannot apply this law in each and every situation. Okay. So inconsistency in Ampere circuital law, and I will show you how this law is not fully correct. Okay.
Okay.
Now see, inconsistency in Ampere circuital law. This is the capacitor. There are two plates of capacitor. This is basically a parallel plate capacitor. So here I have taken a capacitor connected with a battery. A capacitor connected with a battery. So basically, when you will connect the capacitor with battery, there will be the charging of the capacitor.
Yeah. Yes.
Okay, there will be the charging of the capacitor. So due to the flow of the charge, you can say that there will be the current in the circuit. There will be the current in the circuit as battery is connected. There will be the charge on the plates of the capacitor due to the charging. So there will be the current in the circuit basically. So I can say that here also there will be a current. Suppose this is the current I here. So in whole of the circuit there will be the current. So okay. So what I am doing, uh, so what I am doing, I am taking a loop around this. Basically, this is a wire and this is the current. So I am taking a closed loop around this wire. Okay, I am taking a
Okay,
closed loop around this wire, and suppose this is a point X. This is a point X where I want to calculate the magnetic field. Where I want to calculating the magnetic field with the help of the Ampere circuital law.
okay,
Okay. So now at X, when we will apply Ampere circuital law, so at X, when you will apply the Ampere circuital law, so line integral of magnetic field, that is B dot dl, is equal to mu naught times of the current enclosed by the loop. Okay. So suppose R is the radius of this loop. Small r is the radius of this loop. Okay.
okay,
So we can write this as V into 2 pi r is equal to mu naught into I. So magnetic field at point X is equal to mu naught into I divided by 2 pi into r. Suppose this is your equation number 1. So basically, this is the magnetic field at point X. You have calculated with the help of the Ampere circuital law.
yes,
Now, till here, it's all fine. Now I am taking another loop. I am taking another loop in between the plates of the capacitor. In between the plates of the capacitor, I am taking
sir,
another loop. Huh?
I can't
Oh,
see the
just
screen share.
I know, I know. Okay. So here another loop I have taken.
Yeah,
Okay. Another loop I have taken, and uh, this loop I have taken. So
okay, sir.
suppose this point is Y. This point is Y, and again R is the radius of this loop. R is the radius of this loop. So now I want to find the magnetic field at point Y. This is the point
Yeah,
Y. At point Y, I want to find the magnetic field with the help of Ampere circuital law.
yes,
Again, at point Y, I will apply the Ampere circuital law. B dot dl is equal to mu naught times of the current enclosed by the loop. So it will become V into 2 pi r, and mu naught. What is the current enclosed by the loop this time? What is the current enclosed by the loop this time? Is there any current contains by this loop?
no,
Ziyad? Zero current, na?
yeah,
Very good. So when you will put here 0, what will be the magnetic field you will get at point Y? 0.
yes,
So magnetic field at point Y is equal to 0, and magnetic field at point X you are getting mu naught into I divided by 2 pi into R. This is the magnetic field at point X. Okay. So this is your suppose equation number 1 and this is your suppose equation number 2. Now according to the Ampere's law, magnetic at there will be some magnetic field at point X, but there will be no magnetic field at point Y. But then what you do or Maxwell did, he placed a magnetic needle here. Magnetic needle. Okay.
Okay.
What is the use of the magnetic needle? If the magnetic needle will be deflected, means at point X there will be some magnetic field.
Yes.
So here it is seen that this magnetic needle deflected. Magnetic needle deflected. It is seen that.
Yeah.
By the Maxwell. After that, he placed a magnetic needle at point Y. At point Y, he placed the magnetic needle. And what should be the result of magnetic needle? As according to the Ampere's law, magnetic field at point Y is equal to 0. So this magnetic needle should be deflected or not?
It won't deflect.
But he find that it is deflected again.
Oh.
This magnetic needle is deflected. Means if this magnetic needle is deflected at point Y, so at point Y there will be some magnetic field. But according to the Ampere's law, there is no magnetic field.
Yeah.
So we can say that Ampere's law is not fully correct.
Yes, sir.
Experimentally, you are getting some magnetic field at point Y.
Yes.
But when you are applying the Ampere's law, you are getting the zero magnetic field.
Yes, sir.
So basically, this will be the conclusion. At point X, needle deflected, and according to the Ampere's law, there is a magnetic field. At point Y, needle deflected, but according to the Ampere's law, the magnetic field is zero at point Y. So there is a inconsistency in Ampere's circular law.
Yes.
So got it now?
Yes, sir.
Now take the screenshot. So basically, after the Ampere, Maxwell was a great scientist, and Ampere was also a great scientist, but Maxwell proved that Ampere's circular law was not fully correct.
Yeah.
With the help of the experiment.
Done, sir.
See, these are the loops, Amperial loops. Okay, I have told you, Ampere circular law for calculating the magnetic field. We take the loop.
Yeah. Yes.
And then apply Ampere circular law. So for that, you should know how to apply the Ampere circular law. Okay.
Okay. Done, sir. Sir, can you just explain the diagram once again, sir? Only the diagram.
Okay, no problem. This part, na, you are saying?
Yeah. Yes, sir.
Okay, so basically, this is the first. You should know what is this. This is the parallel plate capacitor.
Okay.
This is the parallel plate capacitor, and this is the charging condition of the capacitor. This capacitor is basically charging.
Okay.
So if this capacitor is charging, means there will be the current in the circuit. There will be the current in the circuit. Okay.
Yeah. Okay.
The current will be same like this. I will be the current. Current flows from the positive terminal to the negative terminal like this.
Yes, sir.
So what I have done, I have taken a imperial loop, okay,
Okay, sir.
to calculate the magnetic field at some point x.
Okay.
So this is a point x and a loop is passing through this point x. Okay.
Okay, sir.
Now I have applied the Ampere circuital law here. Ampere circuital law here. That what is that Ampere circuital law? As this is a wire, due to this wire, there will be the magnetic field at this point x.
Yes.
Okay. And
Okay.
at all the point, the magnetic field will be constant. So when you will apply the Ampere circuital law, so Ampere circuital law is B dot dl is equal to mu naught into I.
Yeah.
Okay. So
Okay.
it will become V will be constant. V will be constant. Basically, here this V will be constant and you will do this dl. Okay.
Okay.
So close integral of dl is equal to V into 2 pi r. Close integral of dl means you are adding a small element of this circle and you will get the perimeter of the circle. Perimeter of the circle is 2 pi r. So that is why I have written V is into 2 pi r here. Now after that you have taken a loop. After that you have taken a loop